continue what we learned so far. Review. We start talking about series. We try to analyze series using different tests. Series, then tests for series. We're interested in having convergence series, so we introduce different types of tests to be able to analyze those series. Then we said that, hey, let us make it more interesting. Let us define some new series that we call power series. We talked about power series. We're interested in analyzing power series for their convergence. So we defined R using ratio test to analyze the radius of convergence, the interval of convergence, the radius of convergence. We denoted that by R. Remember that we used our ratio test to find R. Then we said that, hey, this R actually gives, for example, a boundary for X, if A is equal to 0 for X, and suppose this is your R, but it doesn't tell us anything about the boundary values. It says X is bounded between -1/3 and +1/3. What if I plug in X equals to -1/3? Is the series, the original series, convergent? Is it divergent? What if X is equal to +1/3? What we can tell about the original series? So in these two cases, we need to plug boundary values into the series and analyze its convergence. There you go. So we start talking about power series, and then we wanted to talk about Taylor series and special case Maclaurin series. Power series was defined as the sum Cn x minus a to power n starts from 0, goes to infinity, and we saw that by using the ratio test, we can find the interval of convergence, and R is our radius of convergence. By analyzing the boundary points, we either do not include any of these, we might include both of these, or just one of these boundary values. Well, we also said that, hey, for a function like f of x, if we have a function like f of x, and it has a series expansion like this, f of x equals to the sum Cn x minus a to the power n starts from 0 to infinity. There is a connection between these coefficients, these numbers, and the derivatives of this function. So Cn, all these coefficients, all these numbers can be written as the nth derivative of function evaluated at a, center a, divided by n factorial. And remember that you have to include the interval of convergence as well. Okay, let's take a look at one example. Then we go over two theorems and we try to analyze the remainder of function. Let's take a look at one example. For our exponential function, we're going to write down the Taylor series at a equal to 0. We actually have a name for it. We call it Maclaurin series. Example, write Taylor series for e to the x at center a equal to 0. Let's write the note here. Taylor series for a is equal to 0 is called Maclaurin series. So Maclaurin series is a special case of the Taylor series. So when the question says, hey, write Taylor series for e to the x at a equal to 0, means that we are looking for the Maclaurin series. We know that f of x is equal to the sum Cn x minus a to power n starts from 0, goes to infinity, and the absolute value of x minus a, or the distance between x to a, x to the center, is less than r. In this case, our a is equal to 0, so e to the x is equal to the sum Cn x minus 0 to power n, or x to the n starts from 0, goes to infinity. Absolute value of x is less than r. And we define Cn. Guys, the definition is important. You always have to look at the definition. Cn is defined as the nth derivative of function evaluated at a. Our a is equal to 0 divided by n factorial. So e to the x is equal to c sub 0 x to 0, c sub 1 x to the first power, c sub 2 x squared, c sub 3 x cubed, plus the rest of the terms. We need to evaluate each of these numbers, coefficients. So these are just numbers. This is a number, this is a number, this is a number, this is a number, or these are coefficients. So to find c sub 0 is equal to the 0th derivative of function at 0 over 0 factorial. The 0th derivative is equal to the function itself. So this is actually e to the x. Where do we evaluate x? When x is equal to 0. Divided by n factorial, 0 factorial, or just 1. You get e to 0 divided by 1, which is equal to 1. So e to the x is equal to 1 times x to the power 0 plus c sub 1 is the first derivative. N is equal to 1. The first derivative of the function when when the value of the function is equal to 0 divided by 1 factorial. The first derivative of e to the x is e to the x. So e to the x evaluated at 0 divided by 1 factorial, which is 1. Again, we get e to 0 divided by 1, which is equal to 1. 1 times x to the first power plus c sub 2. We continue this process. C sub 2 is the second derivative of function at 0 divided by 2 factorial. The second derivative of e to the x is e to the x. So we're going to get e to the x evaluated at 0 divided by 2 factorial. So you get e to 0 divided by 2, or it is a half. A half x squared plus, if you do the calculation, continue that, you get 1 over 6 x cubed plus the rest of the terms. Well, this is expanded form. This is expanded form. We want to write this in compact form. We need to find the pattern here. X to the power 0, x to the power 1, x to the power 2, x to the third power, x to the fourth power. So e to the x can be written in compact form, sum x to powers. X to powers is super easy to recognize. X to power n, and n starts from 0 to infinity. What do we do with these coefficients? The first coefficient is 1. Take a look at what you had before. It was 1 divided by, it is 1 divided by 0 factorial. So this is 1 divided by 0 factorial, which was 1. So you have 1 divided by 0 factorial. The second coefficient is e to 0 divided by 1 factorial, or 1 over 1 factorial. So this 1 was actually 1 over 1 factorial. The third coefficient is a half. It was 1 divided by 2 factorial. 1 divided by 2 factorial. 1 over 6 is nothing but 1 over 3 factorial. Take a look at the denominator, n factorial. So it means that 0 factorial, 1 factorial, 2 factorial, 3 factorial, and the rest of them are located on the denominator, n factorial. So this is our compact form. So what is the conclusion? The conclusion is that this is the Maclaurin series of function e to the x, or you can say that the Taylor series of e to the x at a equal to 0. This is the Maclaurin or Taylor at a equal to 0 series of e to the x. There you go. A theorem for you. This theorem says, suppose you have a function like f of x. And suppose this f of x can be written as the sum of a Taylor series and another term or some terms, which is the remainder. So this is equal to Tn of x plus Rn of x, where Tn of x is the nth power or nth degree Taylor polynomial. And suppose you have the condition that x minus a is less than r. You have your interval of convergence as well. If the limit, if you take the limit of the remainder, if the limit of the remainder, the second term, the second quantity here, while n goes to infinity, this limit is equal to 0, then f of x is equal to the sum of its Taylor series. On the interval of convergence. So if they have this nice condition, if this condition is satisfied, if the limit of the remainder while n goes to infinity is equal to 0, you can for sure say that f of x actually approaches its Taylor series. Okay, Taylor inequality. So Taylor's inequality helps us to actually find boundaries for Rn and take the limits. Taylor's inequality. Very well. If the higher derivative n plus 1 derivative of your function is less than equals to m. M is just a constant. M is a number. So if the higher derivative, in this case, n plus 1 derivative of function is bounded, it has upper bound, it has lower bound, then to be less than equals to x minus a is less than equals to d. So you have an interval of convergence and d is a positive number. These are the conditions that we have. Positive number. Then we can actually find boundaries for our remainder. Then the absolute value of our remainder is less than or equals to m, this boundary, this constant, this number, divided by n plus 1 factorial times absolute value of x minus a to power n plus 1 over this interval, absolute value of x minus a less than equals to. So Taylor's inequality actually help us to find boundaries for our remainder. So if they have boundaries for our remainder, we can easily take the limit. If the limit is equal to 0, then we can use our theorem. So let us get back to our function e to the x. Okay, give us an example. This example says, prove that function e to the x is equal to the sum of its Maclaurin series. Is equal to the sum of its Maclaurin series. Maclaurin series, it means that you have Taylor series and the center is equal to 0. A is equal to 0. Okay, so let us write down the theorem and the inequality that we just learned. And the theorem says, if you have f of x equals to tnx plus rnx And if the limit of your remainder while n goes to infinity is equal to 0 over the interval of convergence, then f of x is equal to the sum of its Taylor series over the given interval. And Taylor inequality tells us that if you have, for example, function f of x, and then you have the interval of convergence x minus a less than equals to d, and the nth derivative of your n plus 1 derivative of your function is actually bounded by a number, by a constant like m, then we can actually found upper bound, lower bound for our remainder. This is less than equals to m divided by n plus 1 factorial x minus a raised to n plus 1. So this is our Taylor's inequality. If we can find the boundary for our remainder, we can easily find the limit. If the limit goes to 0, we can apply this theorem. So we want to use our theorem, this theorem here. To use the theorem, we need to show that the limit of the remainder while n goes to infinity is equal to 0. So this is our task. I want to show this. But how? We don't know what Rn is. But Taylor's inequality tells us, hey, you can actually find boundaries for your remainder. Now, we need to use the Taylor's inequality, which tells us that if the n plus 1 derivative of our function is less than equals to m on x minus a less than equals to d, remember that d is just a positive nice number, then this concludes that our remainder is actually bounded by m divided by n plus 1 factorial times x minus a to the power n plus 1. What do we have here? We know that we are working with Maclaurin series, which says that a is equal to 0. So wherever you see a, you can just ignore a. Now, we're going to use algebra. There's nothing calculus about this. This is just pure algebra. So let me just write this way, because we don't have a is equal to 0 for us. X is less than equals to d. And here you have absolute value of x raised to n plus 1. So pure algebra. Suppose absolute value of x is less than equals to a number like d. For absolute value of x less than equals d, we can conclude that e to the x is less than equals to e to the d. D is a number, e is a number, this is just a number equals to. So if your x is bounded between two numbers, the exponential function with base greater than 1 is less than equals to a constant. Very well. I found my m. Why is that? since the derivatives of e to the x, they are all equal to e to the x, it means that the n plus 1 derivative of e to the x is this less than equals to the same number, m. Since all derivatives of e to the x are equal to e to the x, we just showed that f n plus 1 derivative of f at x is less than equals to e to the d, which is our n. Okay, perfect. I found in m. So what's next? Taylor's inequality tells us that, hey, now you can write absolute value of Rn less than equals to m, that number, e to the d, divided by n plus 1 factorial, and x to n plus 1. So absolute value of Rn x is less than equals to e to the d divided by n plus 1 factorial absolute value of x to the power n plus 1. Now I'm going to use the theorem. If I show that the limit goes to 0, I'm done. I need a little bit more space, so I'm going to erase this one. And of x is less than equals to e to d n plus 1 factorial absolute value of x to power n plus 1. Now apply the limits. The limit of absolute value of Rn x while n goes to infinity is less than equals to the limit of this quantity. But the limit of this quantity is equal to 0. X, remember that, x is less than equals to d. D is just a number. So this is just a number raised to n plus 1 times another number divided by n plus 1 factorial. N plus 1 factorial goes to infinity much faster than the numerator. The limit here is just 0. Limit of e to the d, absolute value of x raised to n plus 1 over n plus 1 factorial, 1n goes to infinity is equal to 0. So the limit of your remainder is less than equal to 0, the absolute value of the remainder. What's the meaning of that? It means that the limit of absolute value of the remainder while n goes to 0 is equal to 0. We just showed that the limit of Rn while n goes to infinity is equal to 0. It means that the theorem says, hey, e to the x is equal to the sum of its Maclaurin series. Since the limit of Rn while n goes to infinity is equal to 0, the theorem proved this statement.